Motion with air resistance. In most A-level problems, you'll be told to ignore air resistance, or you might be given a figure to take into account for air resistance. Other times you might be asked to deal with air resistance qualitatively, that is, without putting actual numbers to it, but knowing approximately what effect it will have on motion. First, I'm going to look at the situation of a parachutist jumping from a balloon. I've used a balloon rather than an aeroplane, so we don't get any complications due to horizontal motion. We can focus on the vertical motion. First, we need to know that air resistance or drag always acts in a direction to oppose motion, the same as any frictional force, and it increases with the speed of the body. At low speeds, drag is directly proportional to speed, as in if we double the speed, we double the drag, and so on. At higher speeds, drag becomes directly proportional to speed squared, so at higher speeds if we double the speed, we get 4 times the drag, treble the speed, 9 times the drag, and so on. The parachutist has now immediately jumped out of the balloon, and so he initially has 0 vertical motion. He will have his weight acting down, and that will be the resultant force, as there is no air resistance at this point. As there is a large resultant force downwards, the parachutist will accelerate down rapidly. Now, a short time after the jump, the parachutist will now have a downwards velocity. His weight will not have changed, but now he will have air resistance due to his downwards motion. This gives a smaller resultant force, and so a reduced acceleration. He's still getting faster, but at a lower rate. A little bit later, and the parachutist's downward velocity will have increased further. His weight will not have changed, but now his air resistance has increased as his speed has increased, and now the air resistance is equal in magnitude but opposite in direction to the weight. So there is 0 resultant force, and the parachutist will travel at a constant speed. This is known as terminal velocity. At the moment he has no parachute, and so he will be travelling very fast, and he would not survive an impact at this speed. This is at the instant that the parachutist has opened his chute. This will not affect his weight, but the large area of the parachute will give a very large air resistance. This is now larger than his weight, leading to an upwards resultant force. This will not cause him to go upwards, but it will cause him to decelerate rapidly. A short time after opening the parachute, the speed has now reduced. The weight will not have changed, but the air resistance will have reduced due to the lower downward speed. This will lead to a smaller upwards resultant force, and so the parachutist will decelerate less rapidly. Later still, and again the weight has not changed, but now the speed is even lower, and so the air resistance now again equals the weight. There is 0 resultant force, and the parachutist travels at a constant speed again. Only this time, with the parachute open, it will be a much lower constant speed than it was before. This again is a terminal velocity, but at this speed the parachutist is able to land safely. When he hits the ground, the weight will still not have changed, but initially he will have a large upwards contact force, leading to an upwards resultant force, and he will decelerate very rapidly. But once he has stopped, the weight will be balanced by the contact force, there will be 0 resultant force, and he will be stationary. Let's just look at that in the form of a graph. This is a velocity time graph of the parachutist's journey, and it would go something like this. Just to point out some of the main features. The gradient of a velocity time graph gives acceleration. Here at the start we have a very steep gradient. The parachutist accelerates very rapidly. As air resistance increases, the acceleration reduces until here there is zero acceleration. He's travelling at a constant speed. This is the terminal velocity with no parachute. At this point here, the velocity reduces very rapidly, so this must be the point at which the parachute was opened. As he gets slower and slower, the deceleration reduces, as shown by the reducing gradient of this line, and this then is the terminal velocity with the parachute open. This point along here, we have another rapid reduction in velocity down to zero, so this is where he hits the ground. We could work out the distance he'd travelled by calculating the area under this graph. Let's look at how the motion of a car is affected by air resistance. In this situation, the engine force is greater than the drag, leading to a forwards resultant force. This will cause the car to accelerate, bringing in an increase in velocity. As velocity increases, so will drag. The resultant force is simply the difference between the engine force and the drag, and so as drag increases, the resultant force will reduce. Eventually drag will come to equal the engine force and will have zero resultant force. The car will then stop accelerating and will travel at a constant velocity. Let's just see that. So the velocity increases, as does the drag. The resultant force reduces to zero. We know that acceleration is equal to force divided by mass, and in this case the resultant force is equal to the force due to the engine minus the force due to the drag. The more powerful the car and or the lower the drag, the greater its maximum speed. A more powerful car will be able to produce a larger F sub E term here, and a more streamlined car will have a smaller drag force here. Let's now look at graphs of acceleration, velocity and displacement against time for the car. Well, the acceleration gradually reduced to zero. The velocity was increasing, but at a lowering and lowering rate until here it was at a constant velocity. And the displacement would increase more rapidly as the speed increased, but eventually at this point there would be a straight line. This is showing where the car has a constant velocity and so a constant rate of increase of displacement. Air resistance affects the motion of projectiles. If this is the theoretical path of a projectile ignoring air resistance, which I'll just label with a dotted line, like this, then air resistance would always act to oppose motion, leading to a lower maximum height and a shorter distance. Something like this. So this would be the path with air resistance. Let's consider the forces acting on an aeroplane. Well, the engine will provide a forwards force we call thrust, and air resistance provides a backward force, drag. The weight, as always, will act downwards towards the centre of the earth, but the airflow over the wings provides lift. When the aircraft is accelerating, thrust must be greater than drag, leading to a forwards resultant force. When the aircraft is taking off, lift must be greater than weight to provide a resultant upwards force. But while the aircraft is flying at a steady speed and a steady height, thrust will equal drag, lift will equal weight.